Thanks everybody for coming. I see someone's still joining us. Again, thanks, especially you guys joining us on the weekend. We really appreciate. Welcome. Let's see, someone just leave a chat here. Yeah. Welcome, Albert. Okay. So before today's webinar, Dr. Tapp starts his presentation. I just would like to do a brief introduction about ideas, our organization, who we are, and what we do. Okay. IDEAS stands for International Data Engineering and Science Association. And we're a nonprofit organization. Oh, I think it's automatically somehow. Let me replay it again. Okay, go back. And we're trying to, anyway, it's just automatically like to play the slides to the next one. We're just trying to bridge the gap between academia and industry, and we focus on AI, blockchain, big data, machine learning, and everything related to data science. And can I go back? Yeah, IDEAS starts 2016. In the past few years, we host a lot of conference, online webinars, and some hackathon and mixer and local meetups. Here are some pictures from our past events. This is one University of Southern California campus. It's our first Southern California AI and Data Science Conference, 2016. And this one is the New York Blockchain Leadership Connect from last year at Marriott Hotel at Times Square. And this is the one from Chicago Blockchain Leadership Connect at the Hyatt. This is the second year of Southern California AI and Data Science Conference at Pasadena Convention Center. There's more. This one is the 30 years of our Southern California conference. Let me see, someone just leave a chat here. Oh. At Los Angeles Convention Center. And here's more pictures from our past events. We also went to Dallas, Boston. There's more pictures. And we went to some schools, to the local meetups and mixer events. If you guys interested in what we're doing, please feel free to visit our website. It's ideas.sn.org. You can also find us on YouTube, LinkedIn, Facebook. Here's a QR code you can see on the right bottom side of your screen. It's our YouTube channel. All of our previous webinars already upload to our YouTube channel. And you can actually subscribe us really quick. Just head over to our website. Again, it's ideas.sn.org. So you can subscribe us, make sure you receive updates about our future webinar and the conference. Okay, right now I'm going to pass this webinar to today's speaker, Dr. Tapp. At the end of his presentation, we will have a small Q&A session. So if you guys have any questions in the middle of his presentation, please tap your question at the Q&A the window. It's this button located on the bottom. You can see a Q&A. Do not leave your questions on the chatting window. Okay, Dr. Tapp, he will present you guys really some cool stuff, some game theory and blockchain. So thanks again, Dr. Tapp.
Yeah, so thank you. This is based on a talk I gave at the Boston Blockchain Fest in 2018, which was hosted by IDEAS. And So I started this under the Dash core group, but currently I'm working with the ASU blockchain research lab. And so a little bit about me: I'm a Ph.D. in math from Purdue University, specifically algebraic geometry. I'm a mathematician teacher, and we've developed a course, for blockchain course for ASU. And this year, starting January, we've actually officially delivered the course, and we've had our first iteration of the course. So I'm hoping we can offer it again in the fall. So some things I want to talk about are the general math that goes into a blockchain and Bitcoin. I want to talk about the concept of a blockchain just a little bit. That might be a review for some people. Blockchain components and stable Nash equilibrium. So that's where I can start building into kind of how the game theory, I want to say the game theory applies to a blockchain, but it's kind of a chicken and egg type situation. It's because the game theory works out well, then that's why I think we're still talking about blockchains today. If the game theory didn't work out too well, then I would think that a blockchain wouldn't be that useful. So part of what I want to impress is that a lot of what you hear in media and in popular discussions are that like blockchain is important, and in business you hear a lot about blockchain, but I would argue that it's actually the game theory that's really important, and a blockchain is just one way to produce a game theory that has a very good amount of stability. Okay, so here's tools for mathematics and computer science, which in a very broad sense of the term could consider that to be magical. Okay, there's hash functions and applications. An application of hash functions are Merkle trees. Another application of hash functions are Bloom filters, and then we have a public and private keys, digital signatures. That was a very big breakthrough when it first was understood that actually would work. A specific example of public and private keys is the ECDSA. That's the one that's used by Bitcoin and a lot of other cryptocurrencies, almost I think all of them. Inverse Bloom lookup tables are another kind of cryptographic tool that we use, and when we're with data science in general. And I mean, there's certain basically these things are all kind of related. In order for Merkle trees, Bloom filters, or inverse Bloom lookup tables to even exist, we definitely need to understand hash functions and have the ability to use hash functions. Merkle trees are a great example of what we would use a Merkle tree if we wanted to communicate information about a list. We would use a Bloom filter where we would want to communicate information about a set. A list has an order, a set doesn't. And an inverse Bloom lookup table actually communicates information about a set, but it gives you a kind of a more robust information. It can be possible to eliminate false positives that a Bloom filter might give you, and also if you can't identify a few items of the set, an identifier can be provided to tell you which items are missing. And another thing we want to talk about is blockchain, but that's not the focus of this slide. So what is a blockchain? So here's a definition of blockchain in practice. This is kind of maybe in the business world, this might apply. So blockchain is a buzzword used so that people who don't have an understanding of this word would throw money at it at ill-defined projects. So this is one way that I've believe I found this this word used, and I get concerned that people might do this, and so I just wanted to put this definition out there. There's a few more definitions. So another definition, which I'm calling a naive definition of blockchain, is it's information which is secured by hash functions by an ever-increasing proof of work. And this is the property that provides immutability. And after one time I gave a presentation, somebody said, well, it is mutable or changeable, and in some respect it is, but it would actually take a lot of work to make that change. So I think the word immutability applies in a very reasonable sense. So here's a general definition of blockchain. So a blockchain is information that is batched into blocks. Each block includes a hash of the previous block. That's where to form a linear chain. So that's where the chain comes in, and the information in each block provides instructions to update an agreed upon global state. And this is, even though this is a decade old now, this or at least publicly out in the open, we've known about this technology for a decade now, and I definitely wanted to include this definition in this presentation, because this definition is kind of the most general, the one that if you're trying to work on an application, this is the one that could encompass the most breadth of applications. So so I definitely wanted to get this definition out there. Another reason I want to put this definition out there is because this definition doesn't have anything to do with a cryptocurrency per se. It doesn't have to do anything with the particular application of a blockchain, and I want to kind of emphasize that a blockchain is not necessarily a tool that's applied for making currencies. It's a tool that's applied for several applications, one of which might be a currency. So I bolded the words agreed upon, because that is what a blockchain provides that wasn't possible before, or in the literature. Like when this first started, it was generally called the Byzantine generals problem. It's been stated in different ways in the literature, and there's been publications that actually said it was impossible to have computers or actors acting at a distance to agree on information and know they agreed upon that information. And so that's the new piece that's added by a blockchain. Okay, so this applies to non-currency applications. And this definition, if we wanted to think about this in terms of Bitcoin, each block includes the hash of a previous block in a related chain. The information in each block provides instructions to update a global state. So in Bitcoin, the global state is the unspent transaction output set, and then a transaction is really an instruction to say that a value or a money or a unit that's at one address is now changed to another address. So a transaction is actually just an instruction to change, and what it would change is the global state in a general sense, and for Bitcoin, that's the unspent transaction outputs. Okay, so here's another definition. Working definition of blockchain. Blockchain is data batched together in blocks secured by an ever-increasing proof of work, along with all the tools that allow Bitcoin to function. So this is kind of a working definition. There's really a lot of tools that go into Bitcoin, and so this is a working definition. Notice that we could even have a different definition, which would include a private blockchain. And I think there are some valuable applications that businesses might find of a permission blockchain that can be provided by software like Hyperledger. But anyway, so okay, this is basically the definition we use for our course development, because in order to understand Bitcoin, you need to understand the digital signature algorithm. You need to understand how the security works, how the Merkle trees are. Understanding Merkle trees helps understand how simplified payment verification wallets, or SPV wallets, work, and also why SPV wallets have a pretty high degree of security. Okay, and I've given other talks on that. And in the general thing, I'm sorry about that. But in the general, sorry about that. I'm sorry. This is okay. So crazy day at the apartment there. Okay, so okay, let me do the full screen. Okay, so this is what we use for our course development, this definition, because Merkle trees were for, they allow simplified payment verification wallets to work very well. So, so some working blockchain components include consensus rules. That's the rules that allow us to determine whether a block is valid or invalid, and that provides governance. And in some presentations that I give, I focus more on the governance that a blockchain provides. Basically, that's a new application that that goes on there. Sometimes when there's disagreements with governance, there's a protocol fork that can happen, which can result, not always, but it can result in a chain fork. And this is a very fast developing situation and field. So we have a lot more information about protocol forking and chain forking available. You know, even in the past year, there's been so much more. An important concept is scripting, and something I wanted to focus on was a stable Nash equilibrium. So, so these are important concepts, and within the past year, we have a lot more information available for what happens, like not just abstractly, but you know, also in practice, about what happens when a protocol forks and what happens when a chain forks. And so this is kind of new territory for that. So, so first, what is a stable Nash equilibrium? So a stable Nash equilibrium exists in a game when any player that alters their strategy will play at a less optimal strategy. Okay, so this means that, so now first we might want to talk about what a game is, and if you're not a mathematician or you're not familiar with game theory, that might not seem like the most interesting thing, because it kind of might sound like I'm studying chess, which chess is a game, and we could apply game theory to chess, or we could study checkers, and we could apply game theory to checkers. But game theory is very general in process, so we don't have to apply game theory to a game. We could apply game theory to many situations. There could be any type of situation where there are actors that are acting, and sometimes they're called players, but we might just call them actors. And if there's a way that we can decide that after an end of period of time, if somebody did well or did poorly, that's basically a situation where game theory would apply. One example of where we might apply game theory is in a market. We have a whole bunch of actors acting in a market, whether it's a cryptocurrency market or stock market or whatever type of market. There's a whole bunch of actors, and we can judge if an actor does well or does poorly based on how much wealth they accumulate. If they end up with more wealth, they did well. If they did end up with less wealth, they did poorly. And we can judge if one person did better than the other, and we can choose how we want to judge, maybe percentage gain or actual nominal amount of gain. Maybe that's what we would consider to be the winning condition. But game theory applies just generally to life, where we have humans that are acting, ancient agents that are actually making decisions and trying to influence an outcome. Okay, so Bitcoin works at a stable Nash equilibrium. That's one reason that's really the reason we're still talking about it today, and that's a concept from game theory. So now stable Nash equilibrium is actually kind of an understatement, because there's it's even a stronger property, okay? Because with Bitcoin, an attacker with less than 50% or maybe 33% of the network hash power has a vanishing probability of doing better than honest mining by attacking the network. So if somebody, generally somebody's not coming with an overwhelming force to the network, they really can't do any better for themselves if they're trying to make money than if they just enforce the rules the way they're supposed to be enforced. And the 50% Satoshis Paper, that's where the 50% attack came in. And the reason I put 33% in is because there's been new information about selfish mining, and so somebody with 33% could actually maybe tilt the scales in their favor, but they can't just kind of do willy-nilly with the network what they want. But there's a little issue. If somebody was tilting the scales in their favor, they might drive away other actors, and 33% could become more. If you look up selfish mining, the percentage can vary a little bit depending on some other factors. Anyway. Okay, also, basically depending on the chance you want it to work. At 33%, it's certain to work. Also, the attack has a vanishingly small chance of success. Like if you have 20% of the network and you try to attack the network with hashing power, as time goes by, you're probably not going to beat the network, and as time goes by, you get less and less chance to beat the network. Okay. And I wanted to compare this a bit to other games to try to put this in context in a very real way. So to put this in context, another game you might look up is the Iterated Prisoner's Dilemma, and this actually applies in a lot of situations. This is, you can look it up. It's a situation where you have two prisoners or two suspected criminals that are believed to have worked together on a crime, and if they both keep their mouths shut, they'll be charged with a misdemeanor and released. But if one person tells on the other, the person that tells will be released scot-free, and the person who is told on will be convicted of a felony. If they both tell, then they'll both be convicted of a felony. So This is an interesting type of game that doesn't have a stable Nash equilibrium. If the best strategy for them to play kind of as a unit is for both of them not to tell, because they both receive a misdemeanor, and that's kind of the best. But that's not a stable Nash equilibrium, because if somebody, if both are not telling, if one person alters their strategy to tell, then they'll get away scot-free. So they gain from that choice. But again, if they both tell, then they both get hurt bad. So this is a type of situation where it's kind of in your interest to work towards the worst possible outcome for all parties. Anyway, so a tit for tat strategy is a strategy that works well in many cases. So that's for the iterated prisoner's dilemma. That's where you have two people that are prisoner's dilemma. They make a choice, and then there's a result. Then they do it again. Then they do it again. They do it again. So tit for tat is basically start by not telling, and keep not telling until the other person, the counterparty, tells. And if the counterparty tells, you tell the next time. So that's like the tit for tat. And so this strategy, there's not really an optimal strategy, but this is a strategy that works pretty well for the iterated game where you do this over and over. And so that's a cooperative strategy. Anyway, so one reason I think we should look at the game theory is that when we're looking at the way these are working, so yes, we had Bitcoin, it worked on a blockchain, but the Bitcoin developers are working on, or have actually now released, the Lightning Network, and it's still in an experimental phase, so be careful. There are some training wheels in what the code that's released. Definitely stick within those training wheels, but the Lightning Network replaces kind of the main thing, which is the stable Nash equilibrium provided by Satoshi, with a tit for tat solution. So tit for tat is like kind of what we knew about game theory before Satoshi's paper. And so not every situation, you can't apply every situation to every game. You can't make everything into a blockchain and all that. But what Satoshi's paper allowed is for Satoshi's paper allowed for a game to be played where it runs, like everybody that works on it is incentivized to help the network work the way it's supposed to work. And when it does that, it's at a stable Nash equilibrium. If anybody deviates from helping the network work the way it's supposed to work, they'll make less money. They'll have less reward. And the Lightning Network replaces that with a tit for tat solution. Again, they're using some off-chain solutions, so they don't tap into that blockchain that Satoshi did. And what I mean by that is there's channels in the Lightning Network, and you have payments that are sent back and forth and back and forth. And your counterparty in a channel could actually publish it might be to their advantage to publish a previous state of the channel. Maybe in the past they had more money than they have now, so they could probably publish a previous state to the chain, and they would gain for that. So that's just the way the Lightning Network works. Now they knew this when they were designing the Lightning Network. So there's a thing built in that's called a punishment transaction, where the person the party that was cheated by publishing the prior state can prove that there was a future state, and prove that the prior state was falsely published, and then the punishment transaction would basically apply a punishment, take the money from the party that was trying to get more money than they're supposed to. So anyway, Satoshi came up with this paper. It completely changed the game literally. And then with the Lightning Network, they're kind of reverting back to a game that was around before Satoshi provided us this more secure game, if you will. Another thing about this tit-for-tat solution, that's basically when you're deciding to publish a prior state to gain or not, if you're making that decision, it's basically kind of an iterated prisoner's dilemma. You can cheat, you can not tell and possibly get a gain, but if both people tell, you get hurt. It's not exactly a thing, but it's similar. It's a similar situation. Okay, so what wider applications might there be? So finding a very stable Nash equilibriums could have applications to, and the idea when making this slide is that it's not just finding stable Nash equilibriums in a blockchain, it's kind of finding stable Nash equilibriums in life, finding situations that we have. So we could apply, it would be great if we could have very stable Nash equilibriums that would apply to criminal justice. That would mean that, by what that I mean, what if it wasn't really in anybody's interest to try to steal? If they tried to steal, they just wouldn't gain or anything like that. I mean, in the physical world, it's kind of hard to make sure that doesn't happen, but maybe we could try to work past like a tit for tat, where if you do this, I'll do that situation. Foreign policy, I would think that I would like to see nations or governments work at a stable Nash equilibrium. And I kind of think war is kind of a symptom of not being in equilibrium. Okay, also stable Nash equilibriums could apply to social cooperation, as it does in the Bitcoin network and other systems. So I think that studying this game theory is actually pretty ripe in what's happening in the world. Like studying the game theory could actually have huge consequences if we can somehow bring that off the chain. So I'm looking, I don't see any questions, and I do have a few things I want to add to these slides. There's so much happening so quick that I wanted to, you might be able to see my face now. There's so much I wanted to add to this. There's so many things that happen so often. So the way a public blockchain works, you know, Bitcoin Dash or Bitcoin Cash, they all work with the idea that that anybody can participate, anybody can mine, anybody can create blocks, and you know they need to provide a proof of work before they're accepted by the network. But they're really open blockchains, and some businesses have decided that they want to use enterprise solutions like Hyperledger is what we use with the students in our course to produce private blockchains and or permission blockchains. And a permission blockchain could be publicly accessible, it could not be. But a permission blockchain, you basically would need to have kind of a whitelist to be approved to put a new block in the chain. And so the blocks, instead of miners, they might be called generators. And with the permission chain, there's some trust that goes in on those nodes that are generating the new block. So, but in an enterprise solution, if you're a conglomeration of 5 companies and you're trying to keep track of a, you know, a cross-company supply chain, it's reasonable to trust those nodes because those nodes are run by the company that all have the interest in having a correct um, denoting of the supply chain at any given moment. So a permission blockchain like that, you know, has some trust to it, but it's reasonable to allow for that trust because it's kind of like a company's running a database, and well, how you know, you don't have to worry about the company hacking its own database. You have to worry about somebody else hacking the database. And if you are using even a permission blockchain, it's once you have a block in there, and it gets buried, it's difficult to change. So so you don't have to really worry about outside actors hacking your database. I mean, they can hack and pull data out, but they really can't hack and change. And so that has a kind of different game theory where you have some trust. Other recent developments are in the Dash network. You have where the game theory changes a little bit, or perhaps significantly. In the Dash network, you have a release candidate on the testnet right now, which is version 14, which includes what are called chain locks. And chain locks are they're threshold signatures that are produced by trusted nodes, which is kind of weird. They're called master nodes, and so Dash is working to a hybrid, and they're not fully trusted nodes. I had to go through the math to make sure that that one bad actor couldn't ruin the whole thing. So, but Dash has master nodes, and so that gives you some nodes that are kind of identified, made a little higher. In order to have a Dash master node, you have to have Dash that's staked on the network or put away in a given unspent transaction output, and you need to and so people that are running the master nodes have an interest already in the Dash system working the way it should, because they'll hurt their investment if the Dash system doesn't work the way it should. And with chain locks, I think the numbers on it, you can look it up, I believe it's in DIP 3. I think it uses a quorum of 500 master nodes. And then if 60% of those master nodes sign off on this is the valid block, that will lock that block in to be kind of the block, and it will prevent a 51% attack of Satoshi. So, or that was possible in Satoshi's paper. So, Dash is changing the game theory to make it a stronger way. And I remember I went through the probability. It was important to make that a 60% threshold, or certainly not exactly a 50% threshold. A little bit higher makes an actor need to have more nodes in order to be malicious, and in order to have and it makes it have a smaller chance of being successful. So that was a pretty good trade-off right there. There's something. Anyway, so Dash has changed the game theory. Like the Lightning Network has gone back to tit for tat, but Dash has changed the game theory in a way that makes it stronger, and Dash still retains the miners. So I think it's interesting from a game theory perspective to study Dash when 14 becomes live on the network. After 14 becomes alive on the network, because when after that becomes live, then the game theory changes, and for my estimation, it's a much stronger game theory, where you still have the miners, they're still incentivized the same, or it's almost the same way. They're incentivized in the same way to enforce the rules of the network, and then you have some nodes that you can trust somewhat, but there's a very high Byzantine fault tolerance on these trusted nodes producing good information for the network. And once they come up with those threshold signatures, then the 51% chance attack becomes moot. It can't happen. And another thing, if you're interested in this, is to look up the BLS signatures that are used to produce. That's another mathematical tool that are used to produce those threshold signatures, and that's a really necessary ingredient of this. Of the chain locks. Okay, another thing you want to keep, currently what's happening that you might want to keep an eye on if you're interested in game theory is the Bitcoin Cash network. The Bitcoin Cash network, they're working towards implementing what they're calling Avalanche, and that is also basically it's providing a 51%, or it's providing a double spend protection in the, but no, I'm not showing the PowerPoint right now. You should be able to see me. So the with the Avalanche protocol, that's still being worked on, and it's going to come out, but it should make it more difficult to perform a double spend. So that's something that's going to change the game theory. I don't think it's as drastic as what Dash is doing, but it does provide a little extra security. So that's kind of nice. Another thing that's happened recently, like in the last 6 months, is on the Bitcoin Cash network, there's been a Bitcoin Cash, Bitcoin Satoshi's vision split that happened. And, I go around and give these talks and say that the Nash equilibrium is very stable. But when that split was happening, there was basically a little bit of saber rattling that was happening on social media that's, saying that one side was going to make it bad for the other side. The newer side to show off the Satoshi's vision side is going to make it bad for the other side, which is now called the Bitcoin Cash side, was back then. So, when that happened, that was kind of that put Satoshi's paper, Satoshi's theory, to the real test, because basically people with an alternate protocol that they wanted to enforce. Bitcoin Cash was changing its protocol, but then the other people wanted to change it a different way. The Satoshi Vision people wanted to change it a different way, and so they changed it at the same time in different ways. And that this shouldn't be an issue. You would just have two different chains that work, and the people that like one or the other would go on with one or the other. But the Satoshi Vision side actually had over 50% of the network at one point. And so we have Satoshi's paper that's makes the 51% attack basically the only thing can go wrong. And it's basically considered almost impossible to do. But with the situation that Bitcoin Cash and Bitcoin is, the fact that they have the same hashing algorithm, and the fact that Bitcoin Cash has a minority of the hashing power, like less than half, makes the situation possible where enough hash power can be bribed in order to maintain or acquire or maintain 50% of the network, or for whatever reason they have 50% of the network. Something that we've known for much longer is the formation of pools. If you do go back and read Satoshi's paper, which I read it like every year, it's a great paper. You'll notice that there was not the concept that people would band together and form mining pools, and the existence of mining pools changes kind of the dynamic for possibly having a 51% attack. And before the Bitcoin Cash, Bitcoin Satoshi Vision split happened, there was one pool that was, or two pools that were supporting Satoshi Vision, and they had over 50% of the network for some period of time, whether it was an hour or 2 days or 5 days. It kind of threw into question some of the assumptions we make about a 51% attack. And that's so. All right, so that's kind of what I wanted to add to the slides. Kind of new stuff that's happening, things to keep an eye on if you want to study this from a game theory perspective, or I mentioned some other very interesting perspectives that you want to study this. Are there any questions that you have? I think we still have about good 10 minutes left.
Thank you, Dr. Tapp. It's very inspiring presentations.
Oh, thank you.
Any questions from you guys? At the same time, I just you might see pop out a survey window. It's our poll to listen to you guys' opinion, how you hear about us, and what other content you would like to see from us in the near future. Give you guys maybe 1 minute to fill it in.
Okay, so we have a question. Yes, so definitely check that survey. We have a question. Let's see. We have a Ted Tanner and we have Wes Williams. Where does the evolutionary game theory come into play? So is that, Wes, is that in reference to evolution from Dash, or is that in reference to biological beings? And then Ted Tanner, the mechanism design. So which specific mechanism? Or I might not be able to answer that question because I might not be that familiar with mechanism design. So, okay, from complex systems. So, so where does evolutionary game theory come into play? So if we study, I mean, I'm not an evolutionary biologist. Well, I'm armchair interested in evolution. But we definitely have examples from nature where we get order out of chaos, where we have a kind of emergent order that happens with let's see. So yeah, we start with kind of a chaotic system of single cell organisms, and then they change in more or less random ways, but at the same time that results in having very complex organisms, and an extreme. I mean, I think humans give themselves too much credit, but that results in humans and all kinds of things. So we definitely see an emergent order in and I see that survey pop up, so please answer that when you have time. So so we see emergent order happen, and I think that our complex systems that we design might be able to keep that in play, might be able to keep that in mind, so that we have very complicated solutions to problems that we might not be able to understand before. And you see, and that's something that's kind of not related to what we're talking about, but there, it's very popular right now. and in my view is about to pop. Like in the next decade, we're going to see major advances in artificial intelligence, and kind of a precursor. I mean, before artificial intelligence, we had evolutionary algorithms which would come up with solutions that could not be conceived of but just by sitting down and understanding the equations and thinking things through. So that's what I would say to that question, Wes. I don't think I'm qualified to answer the mechanism design question. Feel free to put another question up if you like. One thing I wanted to say about emergent order, you start with something chaotic, and I have some pictures behind me that are made from a double pendulum, which is a chaotic system. There's like a pin at the bottom of it, and so you can. So I kind of like these because they help me think about order coming from chaos, and chaos has a mathematical definition, just like a game has a mathematical definition. So, but that's another topic for another series. So, other questions?
Okay, seems like I see no more questions from audience. Then it's time to say goodbye. Okay.
Right.
Yeah.
Wonderful. Thank you so much.
Yeah. Thank you. Thank you, Dr. Tapp.
I've loved doing this. This is a little bit. I mean, we use Zoom for the course that we give. This is a little bit different format than I'm used to, but I hope you enjoyed it, and I'm looking forward to sharing this with some of my students.
Great. Okay. Also, thanks for everybody, for you guys to attending us, and have a great weekend. Bye, you guys.
Thank you.